Welcome back to the software engineering lecture series. Today we'll talk about software architecture. As you recall, in the last in-person lecture, we have been discussing about requirement engineering, the different components of requirement engineering, like requirement gathering, requirement analysis, and requirement specification. Right after that, I would like to discuss the overall structure of software or product under the topic software architecture. Specifically, I will be discussing about the definition of software architecture, the architectural decisions and key concerns regarding software architecture. The documenting architecture, specifically views, will be discussed, and the different architecture styles that we have been using in the software engineering realm will be elaborated. And finally, I will compare and contrast the problem based or oriented and solution oriented structuring of software components. Before diving into defining the software architecture in general, it's better to define what software is. So we can define the organization of software hierarchically based on their level of scope. For instance, a collection of products, or from the software engineering perspective, a collection of software can be described as under one product line if they share common features. So softwares that share common features but with slight difference targeting to different problem domain are said to be in the same product line or product family. So the degree of abstraction of softwares at this level is very high. Hierarchically, what comes after product line is system or product, and each system is further decomposed into subsystems or modules, and modules can also be called packages or namespaces, but can also be further decomposed into packages, and each package will have one or more classes or objects, if you recall the object-oriented development and modeling concepts. And inside each class and object there are methods. They could be instance methods or object methods or class methods like static methods, and the decomposition can get to the source code level. So from this hierarchical description of the software organization, which extends from lowest level software decomposition to highest level abstraction, software is not one long list of program statements. We can define software as a structure rather than a long list of program statements based on this hierarchical structure. So we can define the above hierarchical structure as a taxonomy, okay? A taxonomy, which does not represent the relationship between parts or components and does not specify the function of each part. It's just general taxonomy of the organization of software from product line to source code. So here the question would be, how can we really do decomposition in a way that describes the function of each part and relationship among them? And also one enticing question here would be, why do we really need to decompose systems into fine-grained components? This we have answered in our previous session, which is in the very first chapter of this software engineering lecture series. We have discussed about the problem domain modeling, and one of the main um, important techniques were divide and conquer approach. And divide and conquer approach, and the principle behind it says decomposing bigger systems into smaller systems lets you to address or tackle the complexity of such kind of systems. So the answer for the question, why do we need to decompose systems, is first to tackle complexity by using the principles of divide and conquer approach. The second one is see if some parts already exist and can be reused. So this is mainly in relation to the principle of reusability. And one more important benefit of decomposing systems in relation to reusability is to let developers focus on creative parts and avoid reinventing the wheel or doing something from the scratch. The other one is to support flexibility and future evolution by decoupling unrelated parts. This means when you decouple unrelated parts, that means not completely unrelated, but parts or components with less coupling, then someone else can separately evolve that part. Okay, this helps the overall software environment to evolve and scale up to the desired state or level. The overall benefit of decomposing systems from the first chapter of this course is to create sustainable strategic advantage, which can be further reflected through all those benefits that I just discussed. So now let's define the software architecture. So software architecture is simply the structure of the system to be or the software to be, which is determined by the high level decisions that we make based on the business strategies or the business functions that we have identified during the requirement engineering phase. So the software architecture describes the parts of the system to be or the components of a given software in general and a relationship among them. And this software architecture design is mainly done at the early stage of software development. And because of that, modifying this at the latter stage is a little bit hard. So the decisions we make for for building or designing a software architecture uh, helps us to use well-known solutions that are proven to work with similar problems. So software architecture basically encourages us to use or helps us to use well-known solutions which are tried and succeeded for other problems. So basically, software architecture um, encourages reusability of components and avoids developing something from scratch. So the other one is the software is not a phase of development. It's not a specific product or a particular phase of the software development process. Software architecture is generally a structure of the system to be a software to be, which is generated from the high level decisions the users made. Let's take this safe home access system. The architectural decisions that we can take while dealing with the safe home access system that we know from the previous chapters is, for instance, we might make decisions on system decomposition, how to decompose the big safe home access system into subsystems like subsystem for device control, subsystem for administration, subsystem for remote data access, and some more. Architectural decisions are also decisions on mapping software to hardware. For instance, here we have decided to map subsystem for device control to some embedded computer. Subsystem for administration is set to be mapped to Office desktop, and subsystem for remote data access is set to be put or installed on smartphone or some kind of web system. Okay. The other decisions that we make while working or designing the software architecture is decisions on the development platform of the operating system itself. Okay, so for mobile applications, it could be Android or iOS. For it could be for Windows desktop applications, it could be for web applications, but we have to decide what operating systems to use as a platform. The other decisions that you make while designing your software architecture is a decision on how to fit the subsystem together. This is more to the architectural style of the software in general, or the relationship among the components in a given software environment. So decisions about hardware, decisions about decomposition, decisions about operating system, and decisions about relationship or architectural styles are made at early stage. So this could be perhaps while discussing the requirements with the customer at the very early stage. It could be, a discussion with the customer on what to buy, what kind of hardwares to buy, what kind of devices to buy, and how the user should interact with the system given a constraint called hardware devices. So these architectural decisions can be made at different levels. As we have discussed, the structure of software, it can be defined at product line, at product level, subsystem level, package level, class level, method level. So the same is true for the architectural decisions, which are the inputs for software architecture. So architectural decisions could be made at the product line level, or product level, or subsystem level, or class level. So one important concept here is that given the current level of a system scope, for instance, it could be product line level architectural decision, then a decision is architectural if it can be made only by considering the present scope. So a product line architectural decision is an architectural decision if it can be made only by considering the product line scope. The same is true for product scope and subsystem scope and class scope. So architectural decisions should focus on high impact, high priority areas that are in strong alignment with business strategy. Okay, so as we have seen in our in the previous slide, uh, software architecture gives much emphasis for reusability of systems. Okay, and its major concern is on how to decompose software into components, how to relate these components. Okay, how to map these components to hardware devices and such so on and so on. So for that purpose, architectural decisions in general should be defined by scope level. Okay, and something is architectural if it can be defined only by considering the current scope, by not narrowing the scope in general. So what are the key concerns of software architecture? The first concern, actually, the very important concern of software architecture is system decomposition. So the concern of software architecture is to decompose a big system into subsystems. So for that, we need to ask some questions like, how do we break the system up into pieces, for instance? That would be the first one. What functionality, processing, or behavior or control to include? Even investigating whether we have necessary pieces or not, investigating whether the pieces fit together or not. Okay. The other concern would be cross-cutting concerns, like broad scope qualities or properties of the system, trying to investigate trade-offs among the qualities or the components that you have identified could be the key concerns of the software architecture. Checking the conceptual integrities of your components is one of the concerns of software architecture, and these in general are very important concerns while working on software architecture. So software architecture provides a set of well-known solutions that are proven to work for similar problems. So as I told you, software architecture is there to enhance or to boost the reusability. That being said, about the key concerns of architectural design or the software architecture design, it's better to give much emphasis for the need to compromise while designing or while deciding architectural decisions. This is mainly due to the fact that the best design for a component might not be best for other components. For instance, if you take car components, it might be best for one car type, let's say racing car type, and it might not be best for other type of car types, other car types, which, for instance, luxury cars. So a single component of a car with similar functionality across different cars, one that works best for one type of car might not work well for other types of cars. So due to this, sometimes it's better to compromise the structural aspects of your software, that means architectural aspects of your software or decisions of your software. So among things that urge you to compromise the architectural decisions, some of them are business priorities, the availability of resources, core competencies, target customers, even the nature of customers, their demand might urge you to compromise your architectural decisions. The competitors' moves also matters in the environment where there is adversary, technology trends, existing investments, and also if there are previous softwares which are released in the product line, then backward compatibility should also be checked, and this will also compromise your architectural decision or impact your architectural decision. That being said, about architectural decisions and software architecture in general, let's now talk about the documentation strategies to software architecture. One of the views to document software architecture is a technique to document modules or subsystems. There are various ways of documenting modules or subsystems. The first one is module decomposition view, which implements top-down refinement by using simple block diagrams. The other one, which gives much emphasis for relationship among components, is dependency view. This describes how parts relate to one another. Look here in this diagram, for instance, you see blocks. Various blocks, simple blocks, are used for representing the decomposition of modules, but also relationship between these modules is explicitly mentioned. So this is enabled by using the view called dependency view. The other most commonly used one, especially for projects, security related projects, especially cyber security related projects, is layered view of software architecture documentation. In this case, it's again dependency view, a special type of or case of dependency view, where only adjacent components affects or impacts the operation of the immediate components. So according to layered view, components are sorted by layer in a way the immediate layer, one layer provides services for the other layer and consecutively likewise for the other components. So in this case, this layer is affected by only this layer, and this layer again is affected by the adjacent another layer. Okay, so this reduces the single point of failure. This also enhances or enables scalability of the system in general, since most components are not very interrelated with each other. Only one component is affected by to the maximum one other component which provides services to it. The other view of documenting subsystems in software architecture is class view. This is also called domain model or class diagram, according to object-oriented approach and object-oriented design in particular. From the component and connector perspective, we can also see some of the documentation strategies. The first one is process view, for instance. So the process view defines a sequence of activities among components. So according to process view, system is represented as a series of communicating processes. On the other hand, concurrency view is there to depict the concurrently runnable components, or to showcase concurrently runnable components in a given software architecture. So this gives much emphasis for the simultaneous execution of multiple components. Shared data view can also be called database view. This is mainly a way to facilitate communication between components through data models or databases. And the last one here is client-server view. Here, components are organized or reorganized as either client or server, where the client component triggers requests and the server component provides or responds to triggered requests by providing services. So we usually used Unified Modeling Language notation for documenting software components. So according to Unified Modeling Language notations, a component has its behavior defined in terms of provided interfaces and the required interfaces. Look, for a server component, it provides interfaces, and for the client, it requires interfaces to accept information from the server. So this is potentially exposed through ports. So this is how Unified Modeling Language represents or sketches or documents components, software components, or software architecture in general. So here you can see this one here, each is a representation of the software component or part of the software. And here we have an interface that describes how the connector connects with the component, and it describes the data format to be transferred from one component to the other component. Here we have a connector. A connector is like a pipe that connects one component with the other component. And further detailed description of the component is described in this manner. So the other concern of software architecture, as we have discussed before, is how to fit subsystems together, that we call it architectural styles. Some of the well-known architecture styles are World Wide Web architecture style, we call it representational state transfer or REST. Unix shell script architecture style, it's very common architectural style, especially for batch processes. We call it pipe and filter architectural style. Client server is also well-known architectural style where components act as client. That means a node that asks for a service, and server, a node that provides service for client components. So this is also well-known and widely used architectural style. The other one is shared database or shared data model-based architectural style. We call it central repository architectural style or database-based architectural style. And multi-tiered architectural style or layered architectural style is also another commonly used architectural style that is used mainly for security projects or software architectures. And also there is peer-to-peer and microservice. By the way, microservice, we have been using microservice architectural styles these days widely. So these are some of the well-known architectural styles while working on designing your software architecture, okay? One thing that we have to underline or know when talking about software architectures is that real software system is a combination of various architectures. For instance, a given software system will have a database or data model. A given software architecture might implement security aspects. For that, it might use tiered architectures or layered architectures. A given system might use HTTP based, architectural styles. Some might use different types of architecture style might be used in a single system. So as you can see here, central repository architectural style is used here for the data model here. As you can see here for the subsystem of remote data access, which is more to authentication and authorization. Layered view or layered architectural style is used. We call it tiered architectural style. And for the other ones, simple component-based architectural styles are implemented. That being said about architectural styles, what constitutes architectural styles should be discussed in detail. So the first thing is component. So components are the building blocks of architectural styles, and components can be defined as processing elements that do the real work. And connectors, the second constituents of architectural style, are there to enable communication among components. They might use different protocols and different mechanisms. Interfaces, again, are connection points for components and connectors. They define where data may flow in and out of the components connectors. And the last constituent of architectural styles is configuration. And the configuration decides the arrangements of components and connectors that latter form an architecture in general. So to see some detailed aspects of each of these connectors or architectural styles, let's first see the hypertext transfer protocol as a connector. This hypertext transfer protocol, or HTTP, uses 4 major operators or methods in order to send data over the network from one component to the other component. The first method is post method. Post method requests the server to create a new resource. On the other hand, get method is used to request the server to read a resource. Put method requests the server to update a resource. And finally, this HTTP protocol has a method called delete, which requests the server to delete a resource. So whenever you want to delete some resource from the server, you have to use delete method or operation. Whenever you want to create a new resource on your server, as a client, you have to send that request through post method. So this diagram shows a basic communication between client and server. A client sends client request message, okay? Then this request will be processed by the server, and ultimately the server will respond a server response message back to the client after some time interval. The other connector that we can discuss while discussing architectural styles is a shared database connector or data model based architectural style. Here you see an entity relationship diagram and crowfoot diagram of the restaurant data model. We have been discussing about the restaurant problem in our previous chapter. So here, since the first model is a relational model, it uses entity relationship diagram that describes an entity or something, some being, by its relation with the other ones. Okay, so this is a simple entity relationship diagram or data model of the restaurant problem that we have been discussing before. And similar functionality but different representation is depicted here by using crow's foot diagram. So this is in general called database-based architectural style, or the connector is the data model rather than some other type of links. The other most interesting architectural style is pipe and filter. So pipe and filter is characterized by two major entities, which are filters and pipes. So the components that we use to now in other architectural styles are called filters, where in filters, computation is undertaken, any type of computation. That means a transform of input to output is performed by entities called filters. So filters are another names for components for other architectural styles. And the connectors that connects between filters, one filter from another filter are called pipes in this case. So a filter is responsible to compute and generate outputs, and a pipe is responsible to transport one output as an input to the second or consecutive filter or component. So the diagram here shows clearly how filters operate. So Unix shell commands are a perfect examples for this pipe and filter operations, since they are sequential and the output of one is input for the other one. We can also sophisticate pipe and filter algorithms by taking inputs from one filter to multiple other filters and likewise. The other very well-known, commonly used architectural style is client-server architectural style. So in this context, a client is a triggering process and a server is a reactive process. So a client is there to request for services and a server is there to provide services for the requesting clients. So basically, a server component offering a set of services listens for requests upon those services. A server waits for requests to be made and then reacts to them. Okay, and when we come to a client component is a desiring component, desiring for a service component. It sends a request at times of its choosing to the server via a connector, and that connector is called in the pipe and filter in the pipe and filter context, we called that connector pipe. Okay, but in this case, we refer to it as a connector. So the computation by the server side is conditional. It might accept the requests from the client or reject it. This diagram basically shows how the server and the client components interact with each other. So here we have a client component. Okay, it has its own interface and it has a connector that connects it to the other components. So this client might connect with other client, or it might connect with a server component. So the server component also has interfaces to accept requests from the clients, and this server component might accept or reject requests from this one, but ultimately this server component, if it accepts requests from the client, will compute and return responses back to the client. This control flow is clearly stated in the below diagram. Here we have a client. A client first packs a request for the network transport. Then this will be transported to the server. The server unpacks the request for server call, or actually the network unpacks it for server call, and the server again computes and packs the response for the network transport, and the network transports it and unpacks it at the stage 4, and the client will use the responded information. The layered architectural style is also a well-known architectural style in software architecture design. It's also called tiered software architecture. It's hierarchically organized software architecture or architectural style, where each layer provides service to the layer above it and using services of the layer below it. So Each layer uses the services below it, and each other layer provides the services to the component immediately above it. So all adjacent components are interrelated via data flow. So there is no way for this component to be affected by this component directly. Okay, it might be affected transitively, but this component is responsible to provide information or responses to this one. And again, this one is only responsible to provide information to the adjacent immediate top component. So because of this, the layered systems reduce coupling across multiple layers. This coupling is reduced because each of these are responsible to provide services for their adjacent components. Okay, this in turn hides the inner layers from all except the adjacent outer layer, thus improving evolvability and reusability. So when you decrease dependency between components or coupling between components, then you will nurture evolvability and reusability. The other well-known type of architectural style is called REST. REST stands for Representational State Transfer. It's an architectural style for designing networked applications. So it's a set of constraints that, when applied to the design of a system, promotes scalability, simplicity, and decoupling. So pertinent to the principles of REST, RESTful systems are built around resources which are identified by uniform resource identifiers or URIs. So clients interact with these resources through a uniform interface. For instance, most of the time, REST-based REST architectural style-based applications use HTTP connector protocols. So, and its corresponding methods like get, post, put, and delete. So the essence of this REST architectural style is that clients and servers communicate with each other by a feature called hypermedia link. So whenever a client sends request to the server, the message or the request will be enclosed with a hyperlinked structure. So when we say hypermedia link, it might mean, for instance, XML based or JSON based or HTTP based formats. So the client sends this kind of informations to the server. The server can directly access the request or can access the links, consecutive links, one or more links, for enriching its understanding of the request in the client's context. The same is true for the server. Whenever the server responds to client requests, it can respond, or it can enclose the responses under different hypermedia links. So this is basically how client components and server components interact with each other in the case of REST architectural styles. So the key principles behind REST architectural style, the first one, as we already said, is that the concept of hypermedia as the engine of application state, or HOS. So HOS is a constraint in REST that emphasizes the use of hypermedia links to drive the application's state and control flow. The other very known principle of REST-based architectural styles is the statelessness of the server. When we say the server in REST architectural style is stateless, which means the client which is sending consecutive requests to the server will not be tracked. That means when a server accepts one request from the client, it will not correlate this request with the request the client sent it to the server a couple of minutes ago. The other most important concept regarding REST, the key principle of REST, is the separation of client and server. So in REST architecture style, the client and the server are separate entities that communicate over the network using different connector protocols. And it communicates, that means components in REST architecture style communicate using uniform interface, and most of the time they use standards like connector standards or protocols like HTTP, which in turn uses methods like get, post, put, and delete. The diagram shown here is a physical model of REST architectural style. So everything here starts from the client. The client will have a user interface that lets the user to put or to write some commands. So the client processes the request, that means organizes the request, and sends it to the server using different connector protocols, usually the HTTP protocol. And the server with data storage and various web resources will accept this request and further process and returns with a response or server response hypermedia link. So both the client and the server communicates messages by enclosing them under hypermedia links, and these hyperlinks could be in HTML form, hypertext markup language form, or XML form, extensible markup language form, or JSON form, or any other form like the protocol that we just saw as an HTTP. So the other very important concept here is that the stateless of the server in the case of REST architectural style. That means no memory about past requests by the client is logged by the server side. That being said about the key principles of REST architectural styles, let's now talk about the benefits of this architectural style. The first benefit of this architectural style is scalability, where RESTful architectures are highly scalable, and this is mainly due to the stateless nature and uniform interfaces it employs. So mainly, as we already mentioned, the lack of server-side state allows distribution and load balancing. The other benefit of REST-based architecture styles is interoperability. That means due to the uniformity of the techniques used for communication, and also, the concept of URI, Uniform Resource Identifier, it's really easy to applications using REST architecture styles to interoperate between or among different components. So compatibility will not be an issue as long as other components are using URIs to identify resources among them. The other important benefit, from REST-based architecture styles, is that flexibility. So this is because mainly REST allows for evolving and changing systems without breaking existing clients. This is mainly due to the hypermedia links REST architecture styles employ. And these hypermedia links, or HOS, enables the components to adapt to changes in the server implementation without disregarding the clients. And one other important benefit of REST-based architecture styles is simplicity. Since they use well-known URI-based or HTTP-based methods for communication, it's easy to understand or design or implement such kind of applications. And this kind of architecture styles are very popular among the web developers. To see to elaborate RESTful architecture styles or REST architecture styles by example, let's see how resource naming is performed in the REST architecture style, in the application where REST architecture style is implemented. So here we discuss this one from two perspectives. One is from the conceptual representation perspective. Conceptually, we can assume, for instance, if we have an employee management subsystem or component, then if you want to operate on that subsystem, for instance, say to insert some employee name, then the kind of operation you do is type of CRED operation. So you can conceptually represent this operation as create inside table employees, which is resource name, arguments like name, name, role, and salary. So for each, we will have corresponding values, as you can see here. So this is basically the conceptual representation of creating a new employee record inside the relation called employees. So you can assume here the client or the user will have an interface to create these arguments. For instance, one text box for the name, one other text box for the role, and some other text box for the salary. So here we will have a component to process this one. We call it client. Okay, client. Okay, sorry for the writing. Then this will be transported to the server component using different connector protocols. One of them could be HTTP based protocols. So when when we come to the second one, which is scenario B, HTTP request messaging carrying the content of the HTML form, which is from this interface, uh, that was used to enter the employee data is shown here. Okay, so here, as you can see, the method, since we are inserting, the method will be post. The host is the server in charge of processing this request from the client. The content type is the type of message that you are supposed to send over the network. The content length is the length of the message type or size of the message type. And this is the values that you are sending over the network by using hypermedia links, as you can see here. So this is how resource naming is performed in case of RESTful architectural style-based applications or communication among them. So the first one, which is A, is a common type of communication, okay? But this communication, like this thing, this operation, is transported to other components or servers, or it could also be repositories by using HTTP-based methods or other methods which are, in adherence to the principles of REST architectural styles. Another enticing architectural style that we have been using recently and that we have been implementing specifically for problems that needs data independence is the MVC architectural style. So M stands for model, V stands for view, and C stands for controller. The model holds all the data, state, and application logic. It's oblivious to the view and the controller. That means the view and controller will not have direct access to the model, but they can only access it through application interfaces. So the model provides application interfaces or APIs to retrieve state and to send the notifications of state change to the observer. And according to the MVC architecture style, the view stands to give user a presentation of the model. So it can get direct access to the model through APIs actually, and renders this accessed model states to the user via some presentation canvas. The third component of MVC architecture is a controller. The controller takes user input and figures out what it means to the model. So the brain of this MVC architecture is the controller, by the way. And the memory of the MVC architecture is the model. And the interface that used to show, the implementation details and everything behind is called view. So the diagram here shows the essence of model view controller architecture style clearly. Here we have a user. So everything starts from the user. The user might do something, and the controller is responsible to listen to whatever is done by the input devices, which are in turn triggered or manipulated by the user. Then the controller, if the input devices mentions or states or urges the change in the state of the model, then the controller will transform this command to the model, so it will change the state of the model. And again, if the input devices tells to the controller the need for update of the view or visualization, then the controller is also responsible to change the display, which is later manipulated by the view. Once the controller changes the model, then the changed model state will trigger another notification to the view stating that something has been changed, and this latter will cause a display by the user side to change, which is in the meantime orchestrated by a view component. So model view controller architecture or traditional MVC architecture is constituted of these three major components. And this really provides data independence since the model, the controller, and the presentation are different. So there are different varieties of these architectural styles like model view presenter, model view template for Django type of frameworks, model view controller is also another one. So there are different varieties of this architecture, but the fundamental concept is data independence. So again, to further describe the control flow of model view controller. Here we use another diagram. Assume here we have a user. A user might do something that creates input device events, and these input device events are controlled by the controller. Its specific component to handle such kind of input device events is called event interpreter. Then the event interpreter might cause the data model or the domain model to change, and this is communicated through the model component of the MVC. Then once the domain model or the state of the model is changed, it will send notification to the view. Inside the view, there is a component called model visualizer that accepts notifications from the model and renders back to the user using some kind of media or canvas. So here, as you can see, different states of the model can be rendered to the same view at different time. So this, we call it one aspect of data independence. When we start our presentation in this lecture, we said there are two ways of perceiving software architecture. One is from the problem perspective, and the second one is from the solution or software perspective. So you can define your software architecture from the problem perspective. That means you can define your software architecture in bottom-up approach or by induction, which again means you can define your software architecture subsystems from requirements directly or from problems directly. That we call it a problem-oriented software architecture design. So as you can see here, for instance, here we have some scenario where there are two major actors, which are tenant and landlord. So the tenant might want to open some door. You remember this, the smart home, the smart door system problem that we have discussed in the previous lectures. So here we can detect a couple of requirements, okay? And these requirements directly correlates with subsystems. So one requirement can create or can help to create one subsystem, or combination of requirements might help to create a given system. So this is called a bottom-up approach or a bottom-up software architecture design, subsystems being derived from the requirements. So that being said about the bottom-up approach of software architecture design, let's see the typical software engineering problems, because we can later define the problem-oriented software architecture design from this typical software engineering problems perspective. So we can define these typical software engineering problems from three major categories or use cases, I would say. The first one is user working with computer system, but assuming the problem domain is virtual. So in this case, for instance, here we will have user. There will be a system in between the problem domain and the user. Okay, here we have the system. So we can create two more causes to see the functionality of or the variety of the problems under this category. The first would be at 1.A, which is the system transforms input document to the output document generally. This is a very simple process. So here we will have a user. The user will ask the system to accept some input. Okay, here is the input. Then the system will transform this input to output. This is one scenario. So we can define a lot of problems, a lot of requirements based on this scenario. So the first requirement from here could be, for instance, map input data to output data as said by given rules. The second variety of this software engineering problem is that user edits information stored in a repository. So here, as you can see, here the flow is hyperbolic. But if you see here, it's more to cyclic. That means when the user gives some command so that the system edits a repository or part of repository, and the repository, as we already discussed before, will notify the system about the update, and the system will later notify the user about the changes made. So this is the second typical software engineering problem under category 1. When we come to the second one, This is another scenario again. Computer system controls the physical problem domain. So here we assume the problem domain is physical and the computer system is autonomous to this problem domain. So in this case, we will cancel the presence or existence of the user. So this is a scenario or a software engineering problem where there is no user, but a system which is autonomous on the problem domain. So here, one possible problem that we can derive from here is that autonomous control, autonomously control a physical object or device. So this autonomous control is granted to the system over the problem domain. The third category of problems, software engineering problems, is computer system intermediating between the user and the problem domain. So here we will have again the user, the system, and the problem domain. So the purpose of the system here is to intermediate between these two. In the first case, for instance, here is when you see this one, the purpose of the system is simply to reflect information from the problem domain. So it's unidirectional. Okay. But when you come to the second condition, the system basically controls the problem domain as commanded by the user. So the system is urged to accept commands from the user. Then, according to the user, it will perform some kind of modification, and this modification will be reflected back to or displayed back to the user through the system. So this is a third. This is the second category or the second software engineering problem under category three of software engineering problems or typical software engineering problems. We can further describe this problem-oriented software architecture design from five-dimensional problem spaces or by using five-dimensional problem spaces. These five dimensions of the problem space describes what we have been discussing so far here with these different conditions. So the first one is, for instance, autonomous control. The first dimension is autonomous control. Okay. The second dimension is simple editing. And the third one is data transformation. And the fourth one is manual control. Okay, which is a little bit different from autonomous control. And the last one is information display. So let's revise what we have been discussing so far according to these five dimensions. So that brings us to the software or solution-oriented structure of software. So for instance, from the transformation perspective, which is this dimension, you can see here, from the transformation perspective, so when we talk about transformation, there must be some input, some computing node, and also some other receiving node of that computation. So for this purpose, we can describe the architecture or the structure of the software by three major components. So the first one is the feeding subsystem. Here you see feeding subsystem. The second one is transformation subsystem. It's a computing subsystem. It performs or it transforms input to output. And the third one is receiving subsystem. So this problem can be defined under the umbrella of transformation or under the dimension of transformation. The other dimension is simple editing. So the user gives some command for a component or a system that is supposed to edit the model or the repository. The model consequently will be edited, and the change will be reflected back to the user. This is the second scenario that we have seen here in 1b. The third scenario under category 2 is regarding the autonomy of your system over the problem domain. So in this condition, from the solution perspective or software perspective, you have a controlling subsystem and a control subsystem. Okay, a controlling subsystem instructs the control subsystem, and changes made by the controlling subsystem are reflected back to the controlling subsystem by the control subsystem. This can be defined from the perspective or dimension of required behavior or autonomous behavior. The third category of dimensions of the problem space in typical software engineering problems is information display. So in the dimension of information display, we can have two subsystems. The first one, the monitoring subsystem, and second one, monitored subsystem. So monitoring subsystem looks for, in the first scenario, for instance, it looks for a subsystem that is subject to be monitored, and which is also usually the problem domain, and this problem domain returns back its state so that the monitoring subsystem displays it back to the user. And the last scenario is the commanded behavior. In this case, we do have two subsystems, one the controlling and the second one controlled subsystem. That's all for this session and for this chapter 2. I recommend you to read more about different architecture styles because we cannot cover them in a single lecture. It might require a couple of lecture series to cover different architecture styles at glance. So for that purpose, I would like to give you an assignment. I want you to conduct systematic review on recent architecture styles, and also to pick one architecture style from the revised ones and prepare a demonstration on how they perform or on how they work. For today, we have covered enough. Thank you.